So in part D, we have a non-uniform rod attached to the pivot as shown in figure 3. We have a negligible friction between the pivot, and we're told the length and the mass density. This is function of lambda. So first we need to calculate the mass of the rod. So what we need to integrate here is really so we need to write up the integral, and then we just need to integrate the mass density function lambda as a function as a dx. So we need to go in small steps of dx, and well, we have to integrate this on the entire length, obviously. So we'll go from 0 to 1.2 of 6 plus 10x dx. So this will simply be 6x plus 5x squared. From 0 to 1.2, plugging in 1.2, we will find that this is 14.4 kilograms. And then we need to calculate the rotational inertia of the rod about the pivot. So this, by definition, this I, simply the integral of r squared dm. So we need to integrate the distance squared of a given point. And well, we can rewrite this as we know that dm is equal to lambda times dr, as that is a small piece of mass, and r here is equal to x, as we have coordinates of x. So this will simply be the integral from 0 to 1.2 of lambda times x squared, and more we know what lambda is. So this will simply be lambda, it's 6 plus 10x times x squared dx. And so we can again just integrate this out. So this will be 6x squared. The integral of 6x squared will simply be 3x squared. Then we have 10x cubed. It'll be 10 over 4x to the fourth from 0 to 1.2. Plugging in 1.2, we get 8.64 kilograms times meters squared.